In this video we're going to focus on ionic bonding. We're going to start off by thinking about how you'd recognise whether something is held together with ionic bonding, so it therefore would have a giant ionic structure. We're going to talk about the properties of substances that are held together in a giant ionic structure. We're going to talk about melting point and conductivity. And we're going to talk about the structure of ionic compounds. We're going to build up into how ionic compounds form as well, and explain all of that in this video. So the first thing to remember is that ionic compounds are held together by electrostatic attraction between positive ions and negative ions. So in other words, this is going to happen when you've got metal ions, and remember that conveniently the word metal has got a plus in the middle of the word, and non-metal ions, and conveniently the word non-metal has got a minus in the middle of the word to remind us of that. So if you've got something like sodium chloride or lithium fluoride, metal, non-metal, it's going to be ionic. It could be magnesium oxide, metal and non-metal, or even sometimes when you've got an uneven number of metals and non-metals, so it could be magnesium chloride or aluminium oxide. As long as you've got a metal and a non-metal, it will be ionic. And as we said in a previous video, ionic compounds are always always have what we call a giant ionic structure. That means they have this three-dimensional lattice structure of ions that are held together by strong bonds. And that word lattice structure is a key word that you should learn. And you describe a lattice structure as a three-dimensional, regular repeating structure of oppositely charged ions, in this case, held together by electrostatic attraction. So that's the kind of thing you might want to make a note of and get on a flashcard. And because of that structure, and because this attraction, this ionic bond, these ionic bonds are extremely strong, and there's lots of them, it means that all ionic compounds have high melting points. They might vary from the several hundreds to many thousands or a number of thousands of degrees, but they all have relatively high melting points compared to simple substances like water, oxygen, or whatever it might be. It's worth reminding you as well that the properties of the ionic compound are not directly related to the properties of the elements they're made from. So magnesium oxide does not bear any resemblance to the properties of oxygen just because it's got oxygen in it, so don't worry about that. As I said, they've got a high melting point because there's lots and lots of strong ionic bonds in that lattice structure, and they require lots of energy to break. So to melt them, to turn them from a solid to a liquid, you've got to break all those ionic bonds. But let's think for a moment about why something like magnesium oxide, we'll look at this in detail in a bit, might have a much higher melting point than something like lithium fluoride. So lithium fluoride is in the hundreds of degrees, and magnesium oxide is thousands of degrees. Now, this is because the ions that they form, and we'll see why later on, lithium fluoride is just like the picture above where we've got 1 plus 1 minus ions, but magnesium oxide turns out that you form 2 plus and 2 minus ions when you form magnesium oxide. And so the bonds are much stronger and require more energy to overcome. And so some ionic compounds have higher melting points than others, because of the strength of those ionic bonds can vary depending on the charge and also the size, but mainly the charge of those ions. Right, so as well as the high melting point, we have to understand about the conductivity of these ionic compounds. Now, as we've already said, the ions are held together in this three-dimensional lattice, plus minus plus minus, and those ions are fixed in place. And if those ions are fixed in place, they cannot move, which means ionic compounds cannot conduct electricity when they're solid. So it's worth making a note of this. They cannot conduct electricity when they're solid, as the ions are fixed in place and cannot flow. The classic wrong answer here when talking about ionic compounds is to mention electrons. Don't mention electrons at all here, just talk about the fact that the ions are fixed in place. But if you heat an ionic compound up like lithium fluoride, or indeed if you dissolve it in water, you break those ionic bonds. Yes, that requires lots of energy, but it can be done. And when you break those ionic bonds, they're no longer held together in a fixed lattice. which means those ions can start to move around. Okay, so the negative ions will travel one way and the positive ions will travel another. I'll draw another picture now. So instead of the ionic compound being held in a lattice, the ions are now separate from one another, or can flow past each other, move past each other. And so you can set up an experiment where you can prove that ionic compounds can conduct when liquid or in solution, dissolved in water. Because what will happen is you can stick a graphite electrode and another graphite electrode into what we call the electrolyte, connect up a power supply and a bulb, switch on the power supply, and you'll find that the bulb lights up. And this happens because the positive ions can flow that way and the negative ions can flow that way. As long as you've got ions that can flow, that are free to move, you can conduct electricity and the bulb will light up. So ionic compounds conduct when molten, which is a liquid, or in solution, because the ions can flow. And the ions can flow because they're no longer held in that lattice, because those ionic bonds have been broken. So you need to know how ionic compounds form. And we can imagine that we could be asked in an exam to think about having, say, a lithium atom. Lithium atoms have 3 protons, and if they're atoms, they're neutral and so must have 3 electrons. And a fluorine atom has 9 electrons and has 9 protons, so again it's neutral and will be like that. Now it just turns out that lithium and fluorine are more stable if they're as an ionic compound, and the way that the ionic compound forms is, first of all, we can think of the electron from the lithium moving to the outer shell of the chlorine. So the metal always loses an electron, and we can link that to the redox topic. Loss of an electron means that the lithium has been oxidized and the fluorine has gained an electron, so it will be reduced. And the outcome is always that you end up with ions with full outer shells. So that what we would always do is to draw the ions underneath the atoms with the electron now missing. So that green line there represents a transfer of an electron. And the lithium atom, remember, had 3 protons, which are positive, and only 2 electrons, which are negative. So plus, 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 and 2 minuses, which means overall it must have a plus charge, and we draw that outside of the square brackets, like so. So 3 pluses, 3 protons, 2 minuses, 2 electrons now, and so it's 1 minus. And the fluorine atom, we would draw, again with square brackets around, well, this was the fluorine atom, it's gained an electron, there's the electron that it's gained. We draw a square bracket around it now that it's an ion, and it would have a minus charge because it's got 10 electrons and only 9 protons. It's got 1 more negative charge than it has got positively charged things. So this is how we draw a fluoride ion. And you could just imagine if you had many of those in 3 dimensions, you'd have that large ionic lattice. But if you wanted to make a compound out of lithium atoms and oxygen atoms to make lithium oxide, so lithium ions are an oxide ion, it doesn't work to simply transfer 1 electron. Now, lithium, as I said, will react to end up with a full outer shell, which means that each lithium can give away 1 electron. Lithium's in group 1, which is why it's got 1 electron in its outer shell. Oxygen's in group 6, it's got 6 in its outer shell. And to form a full outer shell, it will need 2 electrons. So you're going to need 2 lithium atoms, each of which to transfer their electron to the oxygen to make an oxide ion. Instead of being lithium oxide simply LiO, lithium oxide must be Li2O. I'll draw that now. So you can either draw it like this, with the 2 times lithium atoms, like lithium ion, like this, and 1 2 minus oxide ion, or you could draw 2 of those separately, which is probably even better. The same kind of logic can apply if you've got an atom in group 2, which has got 2 electrons in its outer shell, and 2 non-metal, say fluorines, that have got 7 in the outer shell because they're in group 7. To form full outer shells, in this case, both electrons must be lost. 1 electron will transfer to 1 fluorine, the other electron will travel to the other fluorine to make 2 fluoride ions, and so you end up with MgF2. So you'd have an Mg2 plus ion and 2 F1 minus ions. So using this logic, you can work out the formula of any ionic compound. You first of all decide what the charge on the ion would be. The metals will all be plus, but if they're in group 1, like lithium and sodium and potassium, there'll be 1 plus. Or if they're in group 2 or group 3, there'll be 2 plus or 3 plus, like magnesium and aluminium there. If the non-metals are in group 7, they'd have a 1 minus charge to have a full outer shell. If they're in group 6, like oxygen or sulfur, there'd be 2 minus. And you can even get 3 minus ions like phosphatide and nitride, if you're afraid if you see those. And so you can work out a combination of metal plus non-metal that will give you an overall 0 charge. So I gave you the example of sodium oxide before and magnesium fluoride before, but you could get any combination of these. So it could be potassium and nitrogen, let's say, and for that to make sense, you would need 3 1 plus ions, so 3 potassiums and 1 nitrogen. Or if you've got something like aluminium and oxide, you'd need 2 aluminiums to give 6 plus and 3 oxygens, or 3 oxides rather, to give 6 minus. Overall it has to be 0 charge. Okay, so you can work out the formula of any ionic compound like that. There's a lot of complicated things I've just covered in that 10-15 minute or 10-12 minute video. You've got to understand how an ionic compound forms, ideally, but you can get some big marks just by understanding that, I've got the pictures there now, but just by understanding that ionic compounds, metal or non-metal, you end up with a lattice structure, you end up with high melting point, no conductivity when solid, do conduct when liquid or molten. For all the reasons I've discussed. If you get your head around those ideas, you can pick up easy marks without even getting your head around the idea of how the ionic bonds actually form. If you can, though, learn to draw those pictures and draw the ions with the square brackets around them and work out the formula of any ionic compound using this approach, you're onto some pretty big marks and a really important topic. This really underpins everything you'll do in redox and acids even later on, so make sure you get your head around it as best you can. Thanks all.